We ran an AI agent for a week with no errors, no alerts, and no pages. It researched topics, wrote summaries, and filed Jira tickets. Everything completed successfully. Then our billing alert fired. $4,200 for the week on this one agent. Expected, $80. When we dug in, the cause was a single innocent-looking prompt change. Someone had modified a system prompt that caused the agent to include the full conversation history, including all tool call results, in every subsequent tool call. By iteration 8, the agent was sending 11,840 prompt tokens instead of 400. At GPT-4o pricing, that's a significant difference, multiplied across hundreds of runs per day. No exception was raised. The agent completed correctly. It was just taking 30 times the context it needed. This is the failure mode that standard APM tools cannot see, and this video covers how to fix that with OpenTelemetry. Standard distributed tracing gives you spans for HTTP requests, database queries, and cache hits. It tells you how long a call took and whether it failed structurally, status code, exception, timeout. LLM calls need a different set of signals. Token counts, prompt tokens, and completion tokens separately because they have different pricing and different failure modes. Model used GPT-4o versus GPT-4o mini is a 30 times cost difference. Temperature and sampling params. Prompt content or a hash of it for regression detection. Tool call count for agents. And most importantly, finish reason. Finish reason is what catches silent failures. When the API returns finish_reason:length, it means the model hit your max tokens limit. The output is truncated mid-sentence. The HTTP status was 200. No exception was raised. Your error rate shows 0. But the output is incomplete, and whatever downstream process consumes it is now working with a corrupted input. None of these signals appear in standard HTTP traces. That's the gap. OpenTelemetry published official semantic conventions for GenAI operations. These reached general availability in OTel 1.26. They're stable, standardized attribute names that work with any OTel-compatible backend. Grafana Tempo, Honeycomb, Jaeger, Datadog APM. The key attributes are gen_AI.system, the provider, OpenAI or Anthropic or Bedrock. GenAI.request.model, what you asked for. GenAI.response.model, what actually ran. These differ when aliases resolve to new versions. GenAI.usage.prompt_tokens and completion_tokens. GenAI.usage.total_cost_ust, which you compute from token counts and a pricing table you maintain. And GenAI.finish_reason. That last one, response model versus request model, is subtler than it sounds. When you request GPT-4o, the API resolves that alias to a specific model version at runtime. The resolved version has specific pricing and specific behavior. Logging the response model catches when aliases change under you without your knowledge. The instrumentation is about 50 lines of Python. A function called traced_LLM_call that wraps any OpenAI-compatible API call. It starts an OTel span with kind client, sets the request attributes, system, model, max tokens, temperature, and a SHA-256 hash of the prompt messages for regression detection, calls the API, reads the response, sets the usage attributes, prompt tokens, completion tokens, cost, finish reason, actual model used, latency. The finish reason check is where you catch the silent failure class. If finish reason is length, the model hit the max tokens limit. The wrapper marks the span with status code error and adds an event recording the token counts. That event now shows up in your error rate. A failure that was invisible becomes visible. Usage, replace every client.chat.completions.create call with traced_LLM_call. Pass task name, a string identifying the operation, like Jira_ticket_draft or research_summary. That task name becomes a span attribute you can filter and aggregate on. For multi-step agents, you want a parent span for the whole run and child spans for each LLM call and tool invocation. OTel's context propagation handles this automatically. Any span you start inside an existing span context is a child. So you start an agent.run span at the top of the agent loop. Every call to traced_LLM_call inside the loop starts a child span automatically. OTel reads the active span context and nests correctly. When the agent finishes, you set the total cost and iteration count on the parent span. In your trace backend, you now see the full agent run as one trace, with each step as a child. You can see at a glance how token counts changed across iterations. In our case, we would have seen prompt tokens rising from 400 to 11,840 across 8 iterations. One anomaly detection rule: alert if any iteration's prompt tokens are more than 1.5 times the previous iteration, would have fired in the first run. 4 alert rules we added after the incident. Prompt token spike: alert if the 95th percentile prompt tokens for any task type is more than 1.5 times the 7-day baseline. Window of 15 minutes. This catches context accumulation bugs and prompt regressions before they run for a week. Truncation rate: alert if more than 2% of finish reasons are length for any task type. Silent truncation at that rate means corrupted outputs reaching downstream consumers. Cost per task: some costs grouped by the task name attribute. Alert if any task type exceeds your expected per call ceiling. We set it at 5 cents per call. Anything above fires a warning. Model mismatch: log whenever response model doesn't match request model. Aliases resolve to versions. Versions change prices and capability profiles. The prompt token spike rule would have fired 12 minutes into the first production run of the broken agent. We ran blind for 7 days. The killer feature we didn't anticipate: once you tag every LLM call with a task name attribute, you can query your trace backend to break down costs by product feature. We found that ticket_classification was costing 18 cents per hour, and ticket_full_analysis was costing $11.20 per hour. When we looked at which tickets were going through full analysis, 80% of them didn't need it. They were classified correctly at the cheaper tier, but routed to the expensive one anyway, because of a routing logic bug. Fixing the routing bug saved $192 per day. That's not something you find by looking at overall API spend. You find it by breaking costs down to the task level, which requires a task name attribute on every span. Full working code is in blog 269, link in the description. The companion repo at github.com/amticbotdroid/amticbotexamples/tree/main/LLM Observability OpenTelemetry has the complete traced_LLM_call wrapper and a working example with Grafana tempo. If you're running LLMs in production without this instrumentation, you're flying blind on both cost and quality. The tooling exists. It works with backends you already have, and it takes a weekend to wire up. Don't wait for the billing alert.